All right. Yes. Any questions? Anything you want to cover?
For linear programming, do we just need to know how to set up problems, or do we need to understand the simplex algorithm?
Not really. Mostly for, you need to know that you can solve it. There is a way to solve linear programs efficiently. You need to have some ability to understand what constraints are, what modeling is the main thing, what the dual of a linear program is. Well, if we could solve the integer program, we would do it. We can't do it efficiently because it's an NP-hard problem. So, or at least we don't know how to do it. So, integer programming is NP-complete or NP-hard. Simply, as you can see, you can model vertex cover easily with it, right? So, if you want, what is an approximation algorithm? It is an algorithm that runs in polynomial time and gives some guarantee on the solution it produces. So, we know how to solve the linear programming in polynomial time, even though simplex algorithm is not a polynomial time algorithm. There exist efficient ways to solve linear programs in polynomial time.
Integer linear programming or NP-hard?
Yes, because you can model vertex cover, right? Or anything else you want. You can model SAT, you can model not anything else. You can reduce essentially all. It's an NP-complete problem, so you can. It's not so easy to see that it's actually in NP. For the reason that, if the numbers are between 0 and 1, then it is easy to see that's in NP because you just have to. The solution is simply the variables which are 1 and the variables which are 0. While if the numbers can be big, it is not obvious that it is in NP, but it's also in NP. Okay.
Could you go over number 2 from spring of 2016?
Number 2, do I have it? I'm not completely sure. Yeah, if you give it to me, I'll. Okay. Okay. Let's see. Okay. Not sure many of you have seen this. Can everybody read this? Yeah? No? You want me to zoom in? I thought my eyesight is getting a little worse, but you guys are young. Let's see. Zoom. Is it the focus or the... Okay, is it better? Yeah. Okay. She wants to... Okay, it's a long problem, so I want everyone to read it and see what okay, you first you have to, from Jeff's problems, you have to strip away all the extraneous stuff to get to right, you know. So, you know, all that, so there are M soldiers, right, okay, and tasks, right? That's what I'm trying to, I haven't read it, so I'm just reading it online now. So, so M soldiers and tasks, and each task requires a specific set of skills, such as knows what to do in a trench or whatever, right? For each task, exactly K soldiers are qualified to complete that task, okay? Okay, so what are the things that we are, what are the pieces of information, right? There are M soldiers, N tasks, okay? So those are the objects of interest. And what else do we know? For each task, so each task requires a specific set of skills, right? So there are some skills too, right? How many, we don't have a number, but let's call it P skills, right? And I assume that, you know, so for each task there are a bunch of skills that are necessary, right? So what kind of, how do we model that? What problem comes to mind? I mean, don't worry about the problem, but you know, what is the, so how do we represent it, right? Each task you can think of is has a subset of skills, right? If you think of skills as some set, then each task has a subset of skills that are necessary for it, right? Okay? And what else is it saying? For each task, exactly K soldiers are qualified to complete that task. So, okay, you know, for each task there is okay. Unfortunately, Lafayette's soldiers are extremely lazy. For each task, if Lafayette chooses more than one soldier qualified for the task, each of them will assume that someone else will take on the task, and so the task will not be completed. A task will be completed if and only if exactly one of the chosen soldiers has the necessary skills for that task. So Lafayette needs to choose a subset of soldiers that maximizes the number of tasks for which exactly one soldier else is qualified. Okay. So let's think of it like this, right? Well, the tasks finally, the skills don't seem to be necessary. So let's see. These are the you can think of as soldiers, right? And tasks, right? Okay. So let's draw a graph where, you know, there is we connect a soldier to a task if the soldier can do that task. I see. Okay, we'll switch. OxVGA. Okay. All right. So we have soldiers and tasks, right? And we are going to switch the not switch. We put an edge between a soldier and a task if the soldier can do that task. Okay. Now, one of the constraints is that, this is just for the later on, it's not important right now, but it will come up later. For each task, exactly K soldiers are qualified to complete the task. What does it mean? In terms of this graph, what does it mean? Yeah.
There are going to be k images on each of the nodes in the class.
Right. So the degree of each of the task nodes is exactly k, right? Because there are only exactly k soldiers which can do it, right? Okay. Okay. Now what is it that they want, right? You want a subset, right? So you want to pick. Okay, so what do you want to do? You want to pick a subset of the soldiers, right? Okay, so that means that I do this, I do this, I pick some subset, right? Okay. What happens when I pick that subset? Okay. A task. So look at this task. Okay. That task has 2 soldiers we picked, right? Yeah. So that means we don't like that. That task will not be done. Okay. Suppose there is, look at this task. What about that task? Okay, that task has only 1 soldier among the ones we picked, right? So maybe that will be done. If I assign this guy to that, it will be done. Yeah.
Do you need 1 soldier per task, or is it a variable amount for each?
No, 1 soldier per task, right? So it's just that if there are 2 tasks which there is a task for which there are 2 soldiers that are chosen, then it won't be done. Okay. So what do they want, right? Yeah, so okay, so what they want is you first find, if I give you a set of okay, so let's ask the following question. If I give you a set of soldiers that I chose, how will you find the maximum number of tasks that can be done? I gave you this, we have to find the set of soldiers. That is hard, but suppose I gave you a set of soldiers. What kind of problem is that? So I give you a set of soldiers. In this graph, and I say these 3 soldiers are, right? And what should I eliminate? I should eliminate any task which has 2 soldiers that are qualified, no? Okay. So what will I be left with? I look at all the tasks and say, look, I retain only the tasks which have 1 edge to these soldiers I picked. Yeah? Does it make sense? Okay. So in this graph, this graph could be complicated, right? What tasks, so I look at this graph now, right? I pick these 3 soldiers. So what tasks should I retain?
The ones that exist in like a maximum matching.
No. Because remember, I don't want any task which has 2 soldiers I picked, qualified, right? That means, I only retain tasks which have a degree 1 to the. So I'll retain this guy because he has only 1 qualified soldier among the one I picked. If I have 2, that means that I'm not interested in that task. Or 2 or more, right? So I keep this. Do I want to keep this task? Yes, right? Yeah? What about this? No. Do I want to keep this task? No, because that guy is not, yes, that we can't keep that task, right? So we don't keep that task. Who else should we keep? Okay, let's see. I'll make the graph a little bit more interesting. Well, I know I keep this. Sorry. Let me redraw that thing. I'll keep this task because that's only 1 edge, right? And maybe I have an edge like this, and I keep that task, right? I may have also 1 more guy like this, right? So what does the picture look like once I fix the soldiers? I will have I'll retain only tasks which have degree 1 to this side among the soldiers I picked. But I may have, multiple people here, right? So once I have this, how many tasks can I complete? Well, right? How many tasks will I complete? Well, it is not completely clear. Unfortunately, Lafayette soldiers are extremely lazy. For each task, if Lafayette chooses more than one soldier qualified for the task, each other is okay. So then how many tasks will I complete? I'll complete basically all these tasks, right? Right? Okay. So that's what I want to maximize. I want to find a subset of the soldiers so that I maximize the number of tasks which have exactly degree 1 to these guys. Okay, that's an NP-hard problem. Okay, why is it? It's because of set cover. Okay, it is not obvious. Okay, see, in set cover, the really difficult case is when the sets are disjoint. Okay, so in the case when sets are disjoint, you can cover everybody with the collection of sets, and that's the hard part. But don't worry, that's a hard problem. But that's not what we asked to solve, right? We're just it's a setup for a randomized algorithm, right? So what is it that document. Okay, so that's the setup. Okay, so we're saying okay, we are not going to solve that. So instead let's try some algorithm, right? So each soldier independently with probability p. So what are we doing? We are picking each soldier with probability p, right? That's our random solution. Okay. Okay. What is the exact expected number of tasks that will be completed in terms of P and K? Okay. When will a task be completed? If I gave you a set of soldiers, when will a task be completed? If and only if what? Exactly one soldier, right? So, but now I'm picking soldiers randomly. Look at a particular soldier, task. When will it be done? Why will it be done? What is the probability it will be done? What should happen for that task to be done? One of its K soldiers is chosen, right? Exactly one is chosen, right? So that's the problem. It's asking, for a particular task, what is the probability? It has K soldiers, right? It has degree K exactly, right? What is the probability that exactly one of those K guys will be chosen if I am picking each one independently with probability P? What is it? Oh, I mean, no, P, remember P is there. P is the probability that that soldier is chosen. Okay, you have to do that calculation. Don't give me an answer right away, think. So the problem is I'm tossing, there are K people and each person is being picked with probability exactly P. What is the probability that there is exactly one guy that will be picked? Right? So it's like I'm tossing K coins and I want to know what is the probability there's only one head. Right? Or not one head, exactly one head. What is the probability that there is 0 heads? Yeah, but I don't want that, right? I want one head exactly, right? So how will you calculate that? No, if you guys have the laptops in front, the brain is not going to send waves to your head, right? You have to have connection to the paper and pencil, right? And the exam, you don't have laptops in front of you. You have paper and pencil. So write down. It's useful. Think of it as practice.
It's a binomial distribution, right? It would be.
I want a very crisp answer. I don't want. I don't want the answer. I know, right? I want you to get better at doing this fast, so that you don't think too long or worry about its correctness. right? So, right, so just think of it as a practice, right? Yeah, enough time? No? Anybody? Yeah.
P plus 1 minus P to the K minus 1 times
N? No, I just want the probability of one time.
For one task?
Uh.
Then the first part of it.
Oh, repeat it.
P plus 1 minus P to the K minus 1.
P plus?
Quantity 1 minus P.
Oh, P times 1 minus P? No.
Or P plus 1 minus P. Quantity of 1 minus P. To the K minus 1.
P plus 1 minus P to the K minus 1?
Yeah, because I figured they need one soldier. They have K soldiers that can complete it. I left out. Actually, I don't know.
Anybody else? Yeah, this is the right answer, right? Why?
You can pick one of K people.
Yeah, it is K choose 1, right? You can pick K of these people, right? Any of them could be 1. You want exactly one of them to be chosen, right? So I alternately think of this. Suppose the people are 1, 2, 3 up to K, right? What is the probability of this guy being chosen and the rest of them not being chosen? It is P times 1 minus P to the K minus 1, right? Oh, sorry. Okay, so I claim that this is the same as, and why is that the right answer? Because, there are K people. We want to know the probability that exactly one of them is chosen, right? So it could be the first guy. What is the probability that the first guy is chosen and none of them others are chosen? It is p times 1 minus p to the k minus 1, right? Okay. Well, what is the probability that the second guy is chosen and none of the other guys are chosen? P times the same thing. What is the probability that the third guy is chosen? But there are k choices and they're all mutually exclusive, so you add them up. But that's another way of saying the probability of choosing one guy, so you choose the first guy, and then the probability of that event happening is p times 1 minus p to the k minus 1. Yeah? Alright? Okay. Now, what is the expected number? So once I have the probability, what is the expected number of tasks which will be completed? By linearity of expectation, what is it? Times n, right? N times this, right? Don't be shy, right? Okay? But it's good to write it down, right? You say, here x is the random variable which is what? Sum of xi, I equals to 1 to n, right? Where xi is the random variable where the ith task is done, right? Okay, but the xi is a 0, 1 random variable, right? That means that either it is 1 or 0, right? And what is x? X is the total number of tasks that will be done. And they're obviously all dependent, right? x1, x2, x3, xn are not independent, right? Right? Because they may have the same task. But we know by linearity of expectation that that doesn't matter, right? What is the expectation of x? Sum of the expectation of xi, right? That is the linearity of expectation. If you have a random variable which is the sum of other random variables, the expectation of x is the sum of the random expectation of the, that's called the linearity of expectation. Averaging is good. Then no independence assumptions, nothing is necessary for linearity of expectation. But what is the expectation of xi? It is a 0, 1 random variable. It's either 1 or 0, right? What is the probability of, what is the expectation of a 0, 1 random variable? It is probability that is equal to 1. We just calculated that, right? It is k times p, whatever that thing, right? So we just multiply this because there are n random variables, they're all exactly the same, in this case, the expectation is the same, so you get n times whatever the right number is, n k 1 minus, or p 1 minus p to the k minus. Okay? Okay, sorry, I didn't switch. Okay? So x is the random variable which is this, it is sum, okay? So now what is the second question, part of the question? What value of p maximizes the expected value? How should you choose p? How should you choose p to maximize this number? The only thing that matters is what? I mean, n is fixed, right? We can't change n. K is fixed, we can't change k. So the only thing we're trying to choose is how do we maximize p times 1 minus p to the k minus 1? Sorry? Yeah, so what do you get? Let's differentiate, right? Do some calculus, right? So what is the differential of this p times 1 minus p to the k minus 1 when you differentiate with respect to p? Okay, 1 minus p to the k minus 1 plus p times p times k minus 1 there's a minus, right? Okay, yeah, what do you get? 1 minus p to the k minus 2, right? And we set this to 0, right? Find the, right? So what do you get if you do this? Okay, let's assume k is at least 2 for at least this thing. If k equal to 1, what do you get? If k equal to 1, what should you do? Yeah, so that corresponds to what? P equal to 1, right? That's obvious because you just have P. 1 minus P to the K minus 1 is 1, right? Because K is 1 is 0. I mean, K minus 1 is 0. So then you just have P and you maximize P by setting it to 1, right? Let's assume that K is at least 2. Then this formula is okay. Then, we can take out 1 minus P is what you get. What do you get, right? You get 1 minus P is equal to P times K minus 1, right? Yeah, so what do you get? 1 is, you get P is what? 1 over K, right? Yeah? Okay, so if you put that, what do you get? You get, okay, how do I change the page here? Oh. So you get, I get n times k times 1 over k times 1 minus 1 over k to the k minus 1, right? Yeah? So we cancel k, what do you get? You get 1 times 1 minus 1 over k to the k minus 1, right? What is this? Roughly what is it? Yeah, so you have to be a little careful. So it is 1 minus 1 over k to the k, right? It's not exactly k minus 1, right? So divided by 1 minus 1 over k, right? Just keep it, okay? So but this goes to E, so it's basically n over E divided by 1 minus 1 over k, right? Okay? So the last part of the question is asking, can you do that calculation, right? Oh, no, sorry. So what is he asking? He's saying, describe a randomized polynomial time O of an approximation for this thing, right? But this is the algorithm, really, right? Because how many have you done in expectation when you did this? So what does the simple algorithm give you? How many have you done? How many tasks have you done? Roughly in expectation, right? It's at least n over E, no? Yeah? So already, how many can anybody do? At most n tasks, right? And we've already done n over E, basically, right? So this is already a constant factor approximation, right? We are doing a constant fraction of all the maximum potential you can do. Yeah? So just to observe that, this formula gives you basically about n over E. Okay? Yeah? That's it. So the last part is nothing but making sure you understand that this is at least n over E. Yeah? Okay?
So the result has nothing to do with the number of soldiers?
Yeah. Nothing to do with the number of soldiers. So, but you're using the fact very strongly that everybody has degree exactly k. Okay, the problem is more interesting or non-trivial if it is not, right? Okay. This won't work if, say, some have high degree, some have low degree, and so on, right? Well, maybe not. I'm trying to see. Yeah. So, for example, if k is if I take a complete graph, right? Okay. No, that also is okay. If all the degrees are saying if all the degrees are uniform, yeah. So so in some sense, yeah. So this is called in the literature it is called the unique coverage problem. Okay. So what you're given a set cover, right, problem, right, And normally in set cover, what do you want to pick? You want to pick a collection of sets and cover everybody. Okay? And we also saw the maximum coverage problem where you say you can only pick a small number of sets to maximize the number of things you cover, right? Here it's tasks are the elements and the soldiers are the sets. So this is a unique coverage problem where you're saying, I want to pick a collection of sets, and what is your profit? Your profit is how many elements are covered exactly once by that collection of sets, right? So when you pick the soldiers, what is the profit we are getting? The profit we are getting is how many elements have exactly one guy in that set, right? That's the problem, right? So we go back, think of this as where was I? So what we want is think of this as sets and this as elements, right? What are we trying to pick? We are picking a collection of sets on this side. What is it that we get? We get profit. Our profit is how many elements have exactly one guy in this, right? So we are finding we have to eliminate everybody else who has more than one set covering it, right? So it's called a unique coverage problem. Okay, you can, if the degrees are not uniform, then you can do the following trick. You look at, in fact, the analysis will more or less go through if everybody's degree is between k and 2k. Okay, don't worry, this is an interesting problem, I claim that I don't need exactly k for everybody, right? Suppose I tell you that the degree is between k and 2k. You'll still get a constant factor. Do you see that? Let's do that analysis. Suppose everybody's degree is not exactly k, but between k and 2k. It could be k plus 1, k. So what happens? What is the probability that an element is covered? Well, it's no longer, right, we know, what is the probability that an element is going to have exactly one guy, right? It is whatever its degree is, right? Let's say its degree is L. Instead of k, we have, its degree, degree of V times P times 1 minus P to the degree of V, right? Minus 1. Right? This is the probability that an element is covered now, right? Okay? The analysis did not, we looked at only one guy and said what is the probability that, exactly one of them will survive. Well, this is the probability, exactly this probability, right? Okay? So now we know if you want to do the expectation, we sum over all the vertices, the tasks on the right hand side, this quantity. Degree of V times P times 1 minus P to the degree of V minus 1, right? We get that now in expectation, right? That is our expectation, right? So what should we choose P? Well, we don't know what to choose P to optimize if the degrees are wildly varying, right? But if they're between K and 2K, what should I choose? Let's just choose 1 over K, because if everybody is K, we know the right answer is 1 over K. Okay? Alright? Okay, but now my degree is between what? Degree is at least 1 over K, degree is K and is less than 2K. Suppose I choose P to be 1 over K, what do I get? Well, the P is 1 over K, I'll get V belongs to R, degree of V times 1 over K times 1 minus 1 over K to the degree of V minus 1, right? Yeah? What is this value? Well, I know the degree is between K and 1 over K. What happens to this number? What do you think will happen? If it is K, what do we get? We get about 1 over E, right? If it is 2K, what do we get? Let's see. Put it in, right? 2K times 1 over K times 1 minus 1 over K times 2K minus 1, right? Okay? Yeah? Okay, but then what is it? It is 2 times, not 2 times, what is 1 minus 1 over K to the 2K minus 1? 1 over e square roughly, right? So you get, roughly 2 over e square, okay, right? So it's some number between 1 over e and 2 over e square, right? If it is, you can prove that it is something in between and it doesn't, right? So you more or less, you don't get the same number, but it's still a constant for everybody in between k and 2k, right? And so, it's a smaller constant maybe than 1 over e, but it's still a constant, right? So it's fairly robust. It's not exact, we don't have an exact formula, but it is some number between 1 over e and 2 over e square, right? 2 over e square is less than 1 over e, right? Yeah? Because e is a little bigger than 2, right? So 2 over e square is less than 1 over e. That's smaller than 1 over e, so everybody in between will have something in between, okay? And so we get at least 2 over e square. So the expected number of people we cover is at least n times 2 over e square, right? So that's also a constant. 2 over e square is a little bit smaller constant than 1 over e, but we cover most of them basically, right? And you can cover, right? So if the degrees are between k and 2k, you cover a constant fraction, okay? But what happens in a general graph? The degrees are not going to be between a constant factor of each other, right? So what you can do is you can take the degrees and break them up into log n categories. All the ones between degree 1 and 2, all the ones between degree 2 and 4, all the ones between degree 4 and 8, and so on up to n over 2 and n. How many categories are there? Log n categories, right? And then you apply this algorithm to only vertices which have the largest group in those log n categories. One of them should have at least n over log n vertices, right? So you apply this algorithm to those guys and you will cover a constant fraction of them. So from that you can show that we will cover at least n over log n times some small constant. And so we get a log n approximation that way. Okay, that is one, you don't get a constant factor because of degrees, and moreover you can show that that is tight, that in the worst case you cannot do better than that. Okay, but here the degrees are all between, yeah, okay, anyway, that's called the unique coverage problem, right? If you're interested, it's just a fun problem. Okay, all right, I don't want to spend too much time on this, and if you have other questions that I want to get to, yeah. Oh, I don't have them. Okay, everybody understands the algorithm, read the algorithm, okay. Okay, what is it? So it's saying, consider the following randomized algorithm to approximate the smallest vertex cover in an undirected graph. For each vertex V belongs to V, define the priority of V to be the real number between 0 and 1, chosen independently and uniformly at random, right? So what is the thing? We're picking a random number between 0 and 1 for each vertex independently, right? Okay. And we say, which vertices do we include in our set? Any vertex, we look at its a vertex and say, when should we include it in our set? If its priority is the smallest among itself and its neighbors. Yeah? Yeah, so do you see what we are picking? Right, first we pick numbers so let's take a graph. I'm going to switch soon. Okay. So give me some random numbers between 0 and 1 for every vertex. Okay, so you say maybe this is 0.3. What about this guy? 0.5. What about this guy? Sorry? 0.2? Okay, They're not failure. They're not that random, are they? They only have one digit after point, right? They're real numbers. They should have lots of digits. Okay, 0.001. What about this guy? Say 0.015. Okay, something like that. Okay. Then who do we pick? Do we pick this guy? Yeah? Why?
This is larger than 0.2.
No. So what is the algorithm to pick? I forgot.
Pick that vertex if it's larger than one of its neighbors.
Yeah. So, okay. Yeah. Everybody makes sense, understood that. So we pick. No, wait a second. Do you pick this guy?
0.3.
Yeah, why would we pick 0.3?
Because it's larger than 0.2 or 0.001. It only needs to be larger than at least one of the neighbors.
Yeah, okay, that's good. Okay, so we pick this guy. Who else did we pick? Obviously, this guy we pick because he's the largest guy. Do we pick 0.2? Yeah? Okay, we pick this guy. And what else? Okay, all right. Okay, so that's the algorithm, right? You understood the algorithm. So now what? What do you think? So what is the question? First question. So for simplicity, assume that no two numbers are the same, right? If you pick real numbers between 0 and 1, what is the probability that two numbers are the same? Yeah, essentially 0, no? Okay, so let's assume there are no ties. Right? Okay, what is the probability then? What are we picking in this? What is the probability that the set is a vertex cover? Okay, why is it not a vertex cover? When is it not a vertex cover? What does it mean? Yes, so why would we not cover an edge? That means we did not pick either endpoint, right? Why did we not pick either endpoint? How can we not pick both endpoints, right? The only reason we did not pick is that they're equal or something, right? I mean, if one is bigger than the other, we would pick the bigger one, no? Yeah? Yeah? We have to pick the bigger one, right? So the probability is essentially 0, right? That it's not a vertex cover. That make sense? Right? For every edge, if there are no ties, it means we'll pick the bigger one, right? For sure. No? Does that make sense or no? Right? So it's a vertex. It's high probability. It will be. Not high probability. Assuming no ties, it will be basically the measure or whatever you want to think of it. The probability 1, it will be vertex cover. Yeah. Okay. So what is the second part? Suppose the input graph G is a cycle of length n. What is the exact expected size of S?
For A, we can actually say it's 1. We don't need to say like use some type of limit or something.
Okay, so it is basically what is the probability that if I pick two real numbers between that they are equal? Officially it is 0, right? I'm not saying it is tentatively 0. It is 0, right? Well, it's a small subtlety because of you really get into measure theory if you really want to ask me what does it mean, right? But right? Yeah. Okay. Let's put that under the rug, right? Okay. Suppose the input graph is a cycle of length n. What is the exact size of the vertex cover, right? So now we have to ask again, all of this break down into what is the probability that a vertex will be picked? Just one guy, and then it is expectation, linearity of expectation used, right? What is the probability that one guy is picked? So I mean, I'm asking, basically take this graph, right? Okay, take this guy, right? You know, what is the, you know, if I give you this graph and, you know, this guy is like a cycle, right? You know, this is exactly 2 neighbors. What is the probability that I'll pick this guy? Yeah?
He has to be larger than both his neighbors, so 1 in 3.
No, he doesn't have to be larger than both his neighbors. He has to be larger than at least one of them.
So 2, 3. Sorry, 2 over 3.
No, that, yeah, you have to be you have to do that analysis now, right? Now you understand what that you need to analyze. You don't pull out a number. Probability is a little tricky, right? You know, sometimes you add, sometimes you multiply, sometimes you have to think, you know, what is it that I need to analyze, okay? So what is the event that you're interested in? So in a cycle, or, you know, in general, you know, I have k neighbors, say, right? Let's take cycle because it's simple. That's why I gave cycle. I could have asked for any degree guy, right? If I have a 2 neighbors, right? I'm picking numbers independently, right? I'm picking a number for myself, and the 2 guys are picking numbers. When do I not get picked? Maybe that's easier, right? See, I will get picked if my number is bigger than at least one of the other 2, right? I want to know what is the probability that I'll pick myself, right? Say, but okay, maybe that's a little bit harder to understand. When do I not? What is the probability that this vertex is not picked? Well, if its value is less than both of its neighbors, right? So that's maybe easier to, right? Okay. So what is it?
3/4. There's like 6. There's like 6 positions. If you treat it like a partition problem, it can be the first one, and there's 6 possible ways that can be laid out, and 2 of them have one of the numbers be the least of them.
It's a little bit tricky, no? Yeah. So another way of thinking about it, maybe it's a little easier, right? So what happens when you have, see, it's a continuous probability, can be a little tricky, right? So it's the same as saying the following, right? You know, I have 3 or k numbers in, I mean, I'm thinking about 3 guys picking independently numbers between 0 and 1, right? So when do I not pick myself? If I'm the smallest, right? Okay. So every set of numbers defines a permutation on this, right? Or the ordering on this, right? So it's same as saying, you know, I'm going to pick a random permutation of these guys, and what is the probability that I am the smallest of them, right? Yeah, picking numbers between 0 and 1 allows me to sort them, right? And I'm asking what is the probability that I am the smallest of the 3 guys, right? It's the same as if I pick a random permutation, what is the probability that I will be the smallest guy, which is the symmetrically largest guy? What is it? There are 3 elements. How many permutations are there? 6 permutations, right? I mean, right? You know, what is the or the same is basically, in general, if I have k guys, right? You know, what is the probability that the one guy is this fixed guy is the smallest in the permutation, right? There are k factorial permutations, right? Total, equally likely, right? If I fix this guy to the smallest, there are k minus 1 factorial permutations for the other guys, right? So it is k minus 1 factorial by k factorial. Okay, so in this case, it will be 1 over k, right? Which is more intuitive maybe, but It's intuitive, but we have to be a little careful in making sure that our intuition is justified, right? By going slow. So it is 1/3, right? So it's 1/3 probability that I won't pick myself, right? So it is a 2/3 probability that I'll pick myself. So the expected number of guys that are picked is what? N times 2/3, right? Yeah? Okay, you can do it more slowly with real numbers, but it's a little tricky, right? Not tricky, I mean, it's... okay. Yeah, is that clear? Okay, what is C? Suppose the input graph is a star. Okay. So what is if the input graph is a star, what is the vertex cover? What is the vertex cover in an input graph is a star? The center, right? It is exactly 1, right? Okay, now what is the question asking? What is the probability that you get the solution of size 1? When do you get a solution of size 1? I have a star, right? My graph is a star. So when, we know the optimum vertex cover, right? But we are doing a randomized algorithm, right? When will I just choose exactly the center of the star? Which means I shouldn't choose anybody else, right? Which means everybody, whatever is the number of the center, everybody else should have a number which is smaller than that. So what does that mean? It's the same kind of thing we've done, right? We are picking numbers at random. What is the...
It would be when the largest number is at the vertex.
Yeah, that guy is the largest number, right? What is the probability of that?
1 over n.
1 over n, right? So it's the same question with not 2 guys, 3 guys, but now bigger guys, right? Yeah? All right. What is that? Suppose again, okay, well, now we run the randomized algorithm n times generating a sequence. Okay. Okay. Yeah, this is a little trickier, maybe. Okay. Or not really, actually. Okay. So what is the probability that we'll get size 1 guy? 1 over n, right? So what is this question asking? Sorry? You run it several times. How many times should I run before I can be guaranteed that I will get, well, not guaranteed, with high probability I'll get only 1, right? So what is it in terms of tossing coins, what is it asking? So 1 over n is a very small probability, right? Okay. So I have a very small probability, or whatever, I have some probability of a coin becoming head, okay? I mean, in this case 1 over n, which is very small. But how many times do I have to toss a coin before I get heads, right? Okay. Well, I have a very small probability of the head. In this case, it's 1 over n. Whatever n is fixed, some number. But I have to toss it again and again and again before I get the heads, right? If it is very small probability. How many times should I toss? What is the expected number of times I need to toss? Sorry? N times, right? It's, yeah, does that make sense? No? Yeah. So I'm tossing a coin, right? It's a geometrically distributed random variable, right? But you don't have to do all this, it's never useful to remember things like, oh, binomial distribution, geometry. You can do everything by elementary means, right? So basically what are we saying, right? I have, let's do it from elementary means, right? How do you calculate the expectation of how many times do I have to toss before I see a head, right? That's the random variable here is how many times do I have to toss before I see a head, right? If I'm tossing a coin of size with P is the probability of the head coming, right? Yeah? So Well, what is the problem? So let's say, the random variable is x, right? Is the number of times I need to toss before I see a head, right? What is the probability that x equal to I? What does it mean, the probability x equal to I? I have to toss I times to see it, right? That means for the first I minus 1 times I don't see it, and then at the ith time I see it, right? The head, right? So this is 1 minus p to the I minus 1 times p, right? If p is the probability, right? Oh, yeah? Okay? So what is the expectation of x? From the definition, it is some I equal to, in this case 0 is not possible, 1 to infinity in fact, right? Because we may never see it. I times probability x equal to I, right? Yeah, makes sense? Okay, but then that is simply the I equal to 1 to infinity, I times p times 1 minus p to the I minus 1, right? That's the general expectation, right? Yeah? Agreed? This now you have to figure out that this is 1 over p, right? Yeah? This is the standard analysis. Okay, but now he is not asking that. So he's asking, he wants a high probability bound. How do you get a high probability bound? Okay. Well, this one is a little tricky, I guess, if you have not seen this analysis before. What do you think? From Chernoff bounds, what can you say? Okay, you don't even need Chernoff bounds, right? Basically, how long should I do this before I see a heads with some good probability, right? So you want to say, let's pick n, okay? You don't need Chernoff bounds and stuff. You say, what is the probability that I won't see a heads after a capital N steps? I don't see heads after capital N steps. What is the probability?
1 minus p.
Yeah, 1 minus p to the n, right? I want this to be small. Oh, sorry. I want this to be small, right? Okay. How small? Well, we have to choose. Okay, what is our p here? 1 over n, right? Okay. 1 minus 1 over n to the n should be small. Smaller than what? Some value. So he's saying in high probability. So let us put usually when we say high probability, it should be smaller than some polynomial in n. Okay. So what should n be? Guess, just to see, just guess. Hmm? Capital N won't be enough. In capital N times, you will get constant probability. Okay, it's just algebra, no? At this point, it's just algebra. We just take, how do we analyze this? Take logs, right? Yeah? Okay. We take logs on both sides, right? Okay, just to make, that's one way of doing it, but say n, let's say ln 1 minus 1 over n is less than, is minus c ln n, right? Okay? Okay, what is ln 1 minus 1 over n when n is a little big? What is it? I've forgotten calculus, I guess. It's about what? Ln 1 minus x. X is small. It is about minus x, right? Yeah. Okay. Okay, you don't need to know that, but it's good to know these things. It's not bad to know these things. It's useful to know this. Okay, so it is basically what? Minus 1 over n is less than minus c ln n. Okay. Right? So I mean the minus will become, so basically you get, n is greater than or equal to Cn ln n. Okay. Another way of doing it is the following. Okay. Suppose I put n, small n here, what do you get? Forget about this side. What do you get after n equal to small n? After n steps, what is the probability that we won't see a head, right? It is 1 minus 1 over n to the n, right? What is that? 1 over e, okay, not e, okay? Okay, so you have 1 over e. How many times do I have to do it before I get high probability? I mean, that means that the probability is, so it's, if I do it one more, again, see if I, after n steps, the probability of not seeing a head is at most 1 over e. Okay, I want to make it even smaller. How many times, if I do 2n steps, what is the probability that I don't see after 2n steps? 1 over e square, right? And now after 3n steps, how much is it? 1 over e cube, right? So how many times do I have to do before I get that e to the something becomes less than whatever, say n? Ln n steps, right? E to the ln n is 1 over n, right? E to the ln n is n. Okay? Okay? That's it. So this is just giving you a more analytical way of doing it, but if you plug in there c times n ln n, what do you get? It is 1 minus 1 over n to the n raised to the c ln n, right? So that is 1 over e raised to the c ln n. That is e to the ln n is n, so it is n to the c. Right? That's another way of doing it directly without going through calculus. Okay, but see, the thing is, you need to have some understanding of this basic phenomenon that once you get a constant factor, you can amplify it like this, right? It's not, you can see it analytically, or you can see it by just getting used to the fact that many times you've seen this, right? What is the probability that something is not covered? Okay, the probability it is covered is 1 over e. Okay, you do it again and again, it'll amplify, right? So log n comes up for useful reasons, right? Okay. There's also something called the coupon collector problem. How many of you have heard of the coupon collector problem? There's a nice game that I play with my kids, right? It's a small thing. So let me tell you the game so that it's right. The game is that it has some kind of caterpillar or something, right? There are some number of colors, 5 colors, 6 colors, and there's a die with 6 colors. Okay. So each time you toss the die, you get to pick the color of the thing that you have not already seen. Okay. So I have some k colors, right? 6 colors because the die is only of size 6, right? Okay, so when I toss the die, maybe the first time, what will I get? I'll get a color because I've never seen any color. So the first time I get that color, right? The next time I toss the die, what happens? Maybe I get a new color that I have not already had, so I'll get another color. But maybe it is the same color as what I already have. So then I lose my turn, right? So now what happens is that, how many times do I have to toss this die before I see all colors? Okay, so it's called coupon collector, right? I have a bag of n coupons. Okay, each time I pick one at random, okay, uniformly at random, and then if you see a coupon that you've already seen, if I've seen I before, I put it back. Okay, I always put it back, but how many times do I have to pick uniformly at random before I see all n colors, right? It's good to know it's n log n. Okay, it's not hard to analyze. It's called coupon collector. It's roughly how long does it take? It takes n log n time. Okay, that's I'm not saying you should know it, but it's kind of fun to know that it'll take about n log n. Okay. Okay. Any more questions? We just did randomization, I guess. That's okay. Everybody okay? Dynamic programming. Make sure you write what you're supposed to write. Okay. because also we don't have, we give you grades and we leave, I'm out on 15th, right? And you can't come back until next semester saying, I actually meant to write this, but I didn't, right?
Do we get a list of like NP?
Yeah. Usually that's not the problem. The hard part is to figure out the proof. Right? Kind of see what it is, right? Okay. All right, good luck. I think I have office hours tomorrow afternoon, and then, thank you. I think Shalmuli also has office hours. Patrick has today, so if you need help, write and post on Piazza if you need clarification, okay?